Sure, sure, sure.
I just talking to Dr. Pankaj Kumar Delhi. So okay, आप थोड़ा लंच तक घर में रहेंगे ना? ठीक, हाँ 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 ठीक है। बाई चांस अगर बीच में कुछ डिस्कनेक्ट वगैरह हुआ तो मैं कॉल करूंगा। या ओके सर, ओके ओके।
ये क्या बहुत सर?
ये स्लाइड पूरी एंटायर स्क्रीन आपने किया ना, तो पूरा जितना स्क्रीन वो सारा आ जाता है।
ओह, अच्छा, ये भी एक पॉइंट है फिर।
उससे वो तो यहाँ दिख रही होगी ना, वहां नहीं दिखेगी। वहां तो सिर्फ
यहाँ पे भी लोगों को भी तो सिस्टम नहीं हो।
नहीं सीखा। ठीक है, इसको चार्जिंग पे तो नहीं लगाना?
लगाया लगाया
लगा दिया ना, यहाँ भी है चार्जिंग। लाइट कम करनी है
ना भी ठीक
ठीक है ना।
बट यहाँ पे वो है तो ये वाला फिर यूट्यूब, अच्छा एक ही जगह
ये
हो
तो
सकता
वैसे
है।
सर ये तो देखेंगे इसको तो।
नहीं, ये यूट्यूब पे जाएगा फिर। डिस्प्ले सेटिंग ऐसे करने से फिर वो हो जाता है।
स्वैप हो गई ना। जूम मैंने नहीं किया कवरेज। जूम
प्रेजेंटेशन से भी आप लाइव शेयर कर सकते हैं।
प्रेजेंटेशन कर सकते हैं?
हाँ, प्रेजेंटेशन।
वो कैसे करेंगे?
प्रेजेंटेशन में जाइए आप, फॉर एग्जाम्पल। प्रेजेंटेशन।
हाँ अभी देखिए ना पंकज जी।
यूट्यूब यूट्यूब
हेलो।
हाँ, यूट्यूब देख रहे हैं अभी।
या यूट्यूब में देखिए। हाँ आपके कॉर्नर में आ रहा है ना आपका?
नहीं, अभी तो नहीं आया। लाइव में आएगा ना, लाइव में नहीं आया। सेकंड वाला आ रहा है। मतलब कल जो हुआ था डॉक्टर कैलाश वाला वो
क्या
आ रहा
बोल
है।
रहे हैं?
डॉक्टर कैलाश वाला जो हुआ था, दैट इज द ओनली वन विच इज कमिंग।
नहीं 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 नहीं, आई कुड सी।
यूट्यूब पर है ना?
हाँ हाँ यूट्यूब में मैं आई कुड सी। हाँ बट आई कुड सी।
मैं आईपीए का यूट्यूब, हाँ अभी आ रहा है, राइट। अभी आ रहा है।
अभी हमारा
second-
कैमरा भी आ गया।
कैमरा भी आ रहा है और
ये कौन सी रिपोर्ट है?
ये तो इन्होंने ऑन
ये
कर
मैंने ओपन की थी।
तो वो
अच्छा,
वाला
वो
डालो,
वाला हटा
ये वाला डालो।
ये चल रहा है लाइव।
ये
आ
नहीं,
जाएगी, ये आ रहा है इसमें, खुद आ जाएगी।
अच्छा
बता
खुद ही
दिए।
आ जाएगा।
हाँ मतलब ये पहले कैंसिल हो जाएगी।
हम्म। Very good.
टाइम।
Oh, one delay. Looks good. Dr. Mata,
या
everything look good.
ओके।
तो हम लोग भी
तो
साइड में सर भी कर देंगे।
नाउ हाउ मच टाइम इज लेफ्ट? सो ऑलमोस्ट टाइम।
11 o'clock probably will stop. Hello. हाँ जी, हाँ जी।
या या
हाँ
या
हाँ।
सर यहाँ
तो शुड आई स्टॉप द लाइव स्ट्रीमिंग और?
अच्छा, मैंने क्या लिखा? मैं करता हूँ।
स्क्रीन स्टॉप करने इनको क्या?
Sure.
वो सर ही करेंगे, वो तो इनके हाथ में है, हम तो यहाँ से नहीं। हटा दिया। कितने भी कोई फर्क
हाँ, it's fine।
ये तो ठीक है ना। पहले से कुछ प्रेजेंट है वो तो आना चाहिए।
फ्रेश ढाका नहीं है?
सर मेरठ जा रहे
मेरठ, हाँ ठीक है।
अच्छा मेरठ में ही है
हाँ
अरे भी एक दो स्टूडेंट गए हुए हैं
ओके, तो अभी इसको बंद ही कर देते हैं, बिकॉज अभी तो वो चलेगा इंट्रोडक्शन वगैरह।
हम्म
हाउ टू स्टॉप इट देन फॉर द टाइम बीइंग?
But how which
स्टॉप, ये ना।
yes stop
स्टॉप शेयरिंग यहाँ तो वहाँ स्टॉप हो गया ना
ये भी स्टॉप ही कर दो फिर।
we have to simply reduce the screen.
यहाँ से स्केप करना पड़ेगा इसे यहीं से तो होगा स्टॉप का ही नहीं है
इस पे लो
एंड लेट्स हो। हाँ बट ये बेसिकली ये तो वो है कवर, वो शटर डाल दिया आपने।
हाँ शटर पड़ेगा तो ठीक है वैसे एक क्लिक में शटर ओपन
चेंज तो हो रहा है,
एक क्लिक
ठीक
में
है।
शटर अच्छा प्रेजेंटर भी लगा तेरे को प्रेजेंटर भी चाहिए होगा
ओके,
एक बार ओपन करना है इसको प्रेजेंटर काम कर रहा है
अच्छा कौन करो तभी।
ये खुद ही बंद हो रहा है।
नहीं यहाँ से हो रहा है
अच्छा वहाँ से एंटर से दोबारा और बंद हो रहा है
हाँ
किस साइड आगे बढ़ रहा
हाँ ये स्लाइड आगे जा रही है अच्छा मतलब सर को बताना पड़ेगा ये आगे पीछे कितने लिए
हाँ
और इससे पॉइंटर स्टील की
ओ,
और यहीं से अपना फिर चला
ये बता।
और बीच वाले को दबा दिया
बंद हो जाएगी
तो शटर डाउन
बेटर होता है उनके टॉप पे इसी में डाल देते हैं,
इसमें
है ना।
इसी में ही तो है इसमें
अरे
डाल तो
सर
दे
की टॉप नहीं है ना इसमें, डाल दे, नोट भेज दी थी क्या?
कौन से सर
सर की
डॉक्टर कांजीलाल की टॉप।
अभी आपने ही तो किया
नहीं
ये
नहीं,
किसकी टॉक है
ये तो मैं दूंगा थोड़ा,
अच्छा
दो
ये
मिनट का।
आपका है तो
इंट्रोडक्शन
सर की टॉक कहाँ है
वो तो उन्हीं के पास है।
तो इसलिए मैं कह रहा था सर को ले आप
हाँ हाँ ले लो।
सर ये सारे गाने से करा तो मैं भी गया सारे गाने लोग भीड़ बढ़ाते हैं चाय पी रहा है चाय तो लगाई दिया तुम्हारे सामने चाय है चाय वाला है कि नहीं बता दो क्यों मैं चाय है से बहुत कुछ हाँ जलसा हो गया पीछे से देख लेना एक बार वो है ये चीज अपने ठीक है आज ये सेटल है सब
पार्टी बैठ में। ठीक है वो सर किसी किस नाम से आएगी सर?
एस
तो सर
ये क्या है?
ये ऊपर है दो।
कौन कौन पीपीटी कौन है?
पीपीटी फर्स्ट
ना सेकंड बात
पीपीटी सेकंड ये कर लो।
हाँ देख लीजिए डेस्कटॉप पे रख दिए तो उधर ही ऑन
ये
कर
आ गई
दीजिए
ये
दोबारा प्रेस कर दीजिए
हो गया सर।
ओनली फॉन्ट ना
आ
चेंज
गया सर यहाँ भी आ गया।
Yeah, it's oh, yeah, that's fine. Data IP is just from the people. Oh, sure.
मैच कर देता हूँ।
हाँ हेलो नाइस टू सी यू आफ्टर क्वाइट सम टाइम मुलाकात हो रहा है कैसे चल रहा है सब so Sun is doing what is doing now? अच्छा कौन सा अपने डेटा साइंस इधर इधर सब लेते हैं तो थर्ड ईयर में एक साल हो बच्चा मेरे में तो अपॉर्चुनिटी बहुत है तो मैडम देखिए एक नाव का डीपी है वो लास्ट 8 मास से इग्नू है तो मुझे पता है लास्ट टाइम तो कुछ तो तो आया नहीं आएगा 3 लोगों को चल रहा है एक्चुअली 8 मास क्या 8 मंथ से बेसी है बट देयर इज ए रेगुलर अपॉइंटमेंट बेसिस पे टाइम लगता है हाँ वो ऑर्डर 5 साल के लिए ऑर्डर होता है मैडम का तो भी रिटायरमेंट तो ये हो सकता है अभी 27 में है वही मालूम आपको जो पिछली बार आपसे बात अरे हो जाए तो अच्छा है नहीं हो बिजी हो तो ऐसा 70 तक कुछ करना मुश्किल हो अच्छा बट ना करना भी मुश्किल है अभी आप
11 बजे या 11:30 बजे?
11
वो आपके उसमें
Yeah, so initially there will be some kind of like introduction and something. When if you come after 15 minutes, that's also okay.
दोनों मेंशन है।
18% time.
Check my context में।
कितना बजे डिफरेंट पे सर्च होता है अगर फुल फर्स्ट दोनों से ऐसा भी हो मगर ऐसा जस्ट आपको पता है
Yeah, this
यहाँ से तो देखा साइड से दिख रहा है क्या?
एक बार ऐसे हाँ
अच्छा यहाँ से देख रहे हैं ठीक so some people have joined there
Kripa is there
अच्छा
from VRC and then some others are also there.
तो आपको थोड़ा होगा कि
अपनी सेटिंग की
इसके बाद फिर हमें वही करना है
बाकी प्रेजेंटेशन नीचे ओपन है
शेयर शेयर तो है
ऑलरेडी शेयर
बट ये स्क्रीन वन स्क्रीन टू
दोनों से
तो ये चलाना है अभी
पहले आप लेंगे पहले आप
हाँ पहले मैं इसको अभी
first I only introduce you
हाँ जस्ट
and then after that
Then
Dr. Khan.
अभी यार
चलो रहने दो IPA ही अच्छा है। हाँ हमें तो दिखना चाहिए, थोड़ा पता लगे कि पीछे स्क्रीन में क्या आ रहा है। क्या हो चाबी हाँ, मेरे बैग में जो बाहर की बोतल थे उसमें तो बैग तो बंद से बंद कर दी या सॉरी मैंने क्या कहा चला और क्या क्या चला वो कैसे चलेगा फिर एक मिनट क्या एक मिनट Now, can you just do one thing? अभी जो है ना, we how to share the slides. Let's say we are here. हाँ, अभी जैसे अभी सर का कौन सा ये है ना, तो इस समय जैसे कुछ भी शेयर नहीं करना है, then what to do? अभी फिलहाल कुछ भी शेयर नहीं करना तो ये सर वो ऑफ कर देंगे हैं? कुछ भी शेयर नहीं करना तो मिनिमाइज कर तो वैसे भी है नहीं लाइव स्क्रीन पे देख लेते हैं ना वहाँ कितना शेयर हो रहा है पता लग जाएगा हो गया क्या जस्ट मिनट सर कुछ तो थोड़ा इशू है अभी भी टाइम लग सकता है हम करने में शटर का हमारा है शटर से बंद कर नहीं वो भी तो नहीं देखा कहाँ how do I it sets the country of 100 yes का बटन भी नहीं आ रहा ना इसमें नहीं स्टीयरिंग तो मैंने स्टीयरिंग तो स्टॉप कर दी अच्छा मुझे यहाँ नहीं दिख रही लाइव में कि हुई कि नहीं हुई क्योंकि लाइव में मैंने हटाई है तो यहाँ होनी चाहिए क्योंकि लाइव काम नहीं कर रहे थे कनेक्ट नहीं हो रहा अब अपने मोबाइल में देख लो नहीं हो गया
यूट्यूब लाइव में तो है
यूट्यूब लाइव में है
हाँ हाँ
where is that how do I my screen okay now it's there ठीक आ गया ना
हो गया
So, good morning to all of you, and a very warm welcome to this DAE Sir CV Raman lecture 2025, which will be delivered by Dr. D. Kanjilal, who was the former director also of Inter-University Accelerator Center, and my PhD supervisor also, and the PhD supervisor of Professor JP Singh. So it's definitely an honor to have him here at IIT Delhi. So before going towards the talk, I would like to have Dr. Pankaj Kumar, who is a senior scientist at Inter-University Accelerator Center, and he is associated with this Indian Physics Association since 2015, and presently also serving as a secretary of IPA. So he will be telling something about the activities of IPA. And after that, we will have Professor JP Singh introducing the today's speaker, and like I say, followed up by the lecture. So, Dr. Pankaj Kumar.
Thank you, Professor Singh. And I welcome, on behalf of IP, I welcome you all. And it's my privilege that I also did PhD with Dr. Kanjilal. So he has been source of inspiration, and he has done a lot of contributed a lot in the upliftment of Inter-University Accelerator Center as well as IPA. He served as the president of IPA also. So a few slides of IPA. This is just to introduce IPA, Indian Physics Association. It was founded in 1970, and objective is that we IPA work towards the advancement, dissemination, and application of the knowledge of physics. And it has licensing with the national science societies like INSA, NASI, and IPA, IAS, as well as it has international presence. It has done MOU with the American Physical Society, Indian International IOP UK, as well as Italian Physical Society. Plus, it is a member of IAAP PPS, Association of Asiatic Physical Society. So there are 48 chapters of IPA, and we have around 4,500 life members. And activities of IPA are, we have the publication that is called Physics News, and it is published quarterly. And there are special lectures like this one, DAE CV Raman lecture series, PA Pandya lecture, IOP, IPA, Homi Bhava, Cockroach Walton lecture series, and all. And we also conduct young physicist meet for young researchers like you guys, plus free meetings. Plus, there are a lot of awards which are given by IPA. Is that it's not moving?
स्टॉप करके देन
आगे नहीं बढ़ रहा है.
जाएगा स्टॉप शेयर चेक
ये वाला ना? Okay. So the publications are sure. This IPA publication Physics News is available on the website on this address, and otherwise, anyone can write email on this email ID, and we send the soft copy. Actually, all the life members they receive the hard copy also. So these are the award given by IPA, and some of the award are for senior category, like R.D. Birla Memorial Award. These are biennial awards. Murli M. Chugani Memorial Award for Excellence in Applied Physics. P.K. Iyengar Award. Hema Ramchandran Lectureship Award. S.N. Seshadri Memorial Award. S.N. Satyamurthy Memorial Award, Booty Foundation in Theoretical Physics, and Ashwini Dutt Memorial Award in Nuclear Physics. And then we have Best Thesis Award also, Rahul Basu Memorial Award in High Energy Physics, CVK Baba Award in Nuclear Physics, and also in Solid State Physics. And we also do, give award in Olympiad, CL Bhatt Memorial Award for Best Student at Indian Astronomy Olympiad Camp, and IPA Award at International Physics Olympiad Camp. So these are the list of awards. And since IPA is it's a body where physics people are involved, so I invite you all to become member of IPA. So to be member, you have to go on the IPA website and fill a simple form, and then you upload the documents whatever are required, and by paying a small amount you will become IPA member. So this is the present executive council. So we have first female president of IPA, and then we have uh, other members, and then co-opted members are also there. And we also work in a gender, for female, especially to address their issues related to gender parity in physics profession, where we have a team which is nominated by the president. And then this award, like one today, this is given by, every year we conduct this award, and it's given by eminent scientists in past, like APJ Abdul Kalam, R. Chidambaram, and Dr. B.V. Sri Kantan, and Anil Kakodkar, Professor G.K. Mehta, A. Kasturi Rangan. So all these awards are, this lecture is highly prestigious. This is sponsored by Board of Research in Nuclear Sciences. And so let's move towards today's lecture. Thank you.
Hey, very good morning to all of you. And it's my honor to welcome Dr. Kanjilal, who was my PhD supervisor. And before actually introducing him, so let me just share one or two sentences about my personal experience with him. So it was really I was fortunate to do PhD under his supervision. And so one thing which I learned, which was actually really very useful, was basically the technical things, scientific and technical things, which was for an experimentalist, which was very difficult. And this kind of environment which we got, which we had at IUAC, that was very excellent that time, and I learned a lot in the technical terms as well as scientific, but technical really it was very hard actually. So Dr. Kanjilal is like one of the best scientists in our country who is involved in accelerator research, and there are very few scientists who knows in-depth knowledge of accelerator, and I can rate Dr. Kanjilal as one of the best person in having the in-depth knowledge of accelerators. And he has taken basically the accelerator research for material science also. That was a very big initiative, because and now we have a very big database of a lot of researchers who are doing research in material science in India actually. And that was in university system also, that was not very well available to the university users. So that was one of his big achievement actually. So he has accelerated research of material scientists in our country. And he was actually so he joined Inter-University Accelerator Center, former it was known as Nuclear Science Center, in 1985, as one of the founder scientist at very beginning. And then he was the person who was involved in the development installation of 15 million volt pelletron accelerator there. And later on, that activity was also expanded when he was actually director also. So like different kind of accelerators were also taken into account. So he actually supervised more than a dozen PhD, like a lot of PhD students, like, and he mentored research activities. He has more than 400 publications in about like having like more than 10,000 citations. And so now he became after like completing the directorship at IUAC, which like in 2018, then he became now a DAE Raja Ramanna Fellow. So he is also elected Fellow of Indian National Science Academy and National Academy of Sciences in India. So with this actually like the brief introduction, I would like to invite Dr. Kanjilal for DAE Sir C.V. Raman lecture 2025. So the title of his lecture is Development of Modern Ion Accelerators and their use in Material Science and Precision Isotopic Quantification. So I again invite Sir for his lecture.
हाँ हाँ अच्छा अभी चालू
हेलो हो गया
बीच में था ना तो सुपर कंडक्टर सपोर्ट वो भी चालू हो गया
अच्छा अच्छा
लेजर पॉइंटर देंगे तो यही रहेगा because online people will not be able to see this pointer.
कहिए सर
No, no, ये ऊपर है ना ये नहीं है पीपीटी में जाओ ये है ऊपर ये रहेगा और
बन जाएगा यहाँ सो रहा है वहाँ नहीं आया सर
लेजर पॉइंटर देखना इधर इधर से
इधर भी है इधर से तो माउस से चलेगा अच्छा सर लेजर पॉइंटर चाहिए
वो इजी होगा लोगों को देखने के लिए
जी हाँ ठीक लाइव नहीं आ रहा
लाइव में
उनको
लाइव में नहीं देख पाएगा जो देख पाएगा
नहीं वो सर चेक कर रहे हैं आया सर लाइव
संदीप Pipama, can you see this?
Yes, but it can
Now I have taken this pointer. This pointer can be seen, no? This pointer.
वही रख दी
Can you see the slide title of the talk?
आप यही रख दीजिए छोड़ दीजिए
slide no I see IPA slide
वो पता नहीं कैसे दे रही
are you using a separate computer or something like that
Now on our screen I have seen my slide, but probably they have to connect.
पीपीटी देखा उसको बंद ही कैसे
उसको बंद कर
पीपीटी कौन सा था
share.
yeah IPA slide is maybe you would unshare and share
ये बंद करना
ये बंद कर दिए एक ही रखी है सब
अभी दोबारा से स्क्रीन शेयरिंग है अच्छा स्क्रीन शेयरिंग
अच्छा सब ए छोड़ के सब एक बंद कर दी
Screen share on. सर बंद करो दोबारा से बिकॉज ये प्रॉब्लम यहाँ को दिखा रहा है ये प्रेजेंटेशन बंद कर सारा बंद कर हाँ, अभी अभी वो खोलो जूम नाउ से ये वाला नाइट से हाँ उसको फुल स्क्रीन कर दो
Yeah, now I can see the slide.
okay full screen do you see full screen also Dr. Mahata
No,
Not yet.
not full screen yet. Yeah.
is it okay now
No.
Yes,
Yeah.
it is now fine.
okay fine
Can you repeat this?
But Dr. Pankaj, again that
Yeah.
right hand side, no, that small that
that is close
icon kind of thing, no, is coming. So
अच्छा
it is a
एक
full
मिनट
screen, no, it is small, and the right hand side, that next slide is icon is there. So do the same thing earlier what you did, no?
हाँ I did it from here but ये कैसे जाएगा
No, वो तो pointer चाहिए, pointer.
नहीं वो यहाँ जाके करना पड़ेगा डिस्प्ले डिस्प्ले नहीं ये डिस्प्ले एंड डुप्लीकेट स्लाइड्स
डुप्लीकेट कर देते
हाँ डुप्लीकेट कर is it okay now Dr. Mahata
Now,
Yes,
yeah,
it is
now
fine.
okay. Yeah.
Please start.
एक बार
Next
Yeah, continue, yeah.
pointer is
पॉइंटर मैं लेता हूँ
ये
Can you see the pointer? Yes.
Yes,
Yes, Dr.
yes.
Kanjilal, please
Yeah.
start. Thank you. Okay. So, and I think slide change, let me see. Slide change I have to do it this one.
ये वाला वो है दिस इज लेजर ऊपर वाला दिस इज ऑन ऑफ एंड दिस इज ब्लैंक
This laser they will not see. That is why I will use the pointer. Okay. Okay. Thank you. And good morning, everybody. So I'll put my talk in a way so that everybody gets something to take home. And I'll emphasize as per the development of modern accelerators. There are many accelerators. In fact, there are more than 30,000 accelerators in the world, and India also having more than 100. So I'll go modern ones which have come up recently, last few decades, last 3 decades, 4 decades, like that, mostly. And some of the physics we do with this or other people are doing. And I will confine to the accelerators in medium energy range. I will not go to CERN or some big accelerators because that will take a lot of time. We have to finish it in certain time. Every talk should finish with reasonable time. So considering that, so let me go with this acceleration. We start with the very basic. Acceleration, always we do with an ion source. This is a typical one, popularly available in the net. And so with ion source produce ions, but there are a lot of background ions. A lot of species are there sputtering from the system. So we need a filtering. First we focus to some point, taking an angle lens or some electrostatic lens, and we analyze, mass analyzed, and particular ion we choose, then accelerate across it. And sometimes we accelerate here also some implanter, and then analyze it. That needs a bigger analyzing magnet. If one can afford it, that is a better option. It needs some money. More energy, bigger is the analyzing magnet. So reasonably, we had some money, so we generally do this acceleration at the beginning for implanter and analyze after that. And then ions are scanned. Beauty of ion having an energy is that it doesn't just like a sputter, thin film or something. It doesn't get confined to the surface. It can penetrate inside. More energy we give, more penetration is there. It can be exactly calculated, and within sort of nanometer, it is reasonably accurate if ion dose is less. If dose you increase, then it has to diffuse around. It goes settled within certain limit with a peak. That also can be calculated. So this is the way devices, sensors, lot of things are being made and miniaturizing the devices by proper masking and scanning the ion beam. They are done, and they are in the market. They have been that is going on for quite some time. And but beauty is that with this kind of thing, this is one of the examples here. India also in Surat and area, we make a lot of money, and we can give any color by doping, choosing an ion doping species, and we can give color to the facet. It is done in the so-called corundum, and then when the kind of chromium or what kind of ion we are giving, accordingly color comes. And there are this is very popular, one of the applications where hundreds of crores the companies are making. In fact, internationally, billions of dollars, and India is quite prominent in this field. In fact, next week also I'm going Surat. They discuss with us and they make, because this is a making money and science is done already known. And anyone is interested, you can go around and see. I cannot go much deeper than this. Only thing is that dopant can do not only devices, it can in color centers and all those things. Some uses are there now. You might be hearing NP center and quantum bit. This is also being done. But to come to the basic physics of it, this simulations, all this is a simulated cloud. And in fact, beauty is that this I have put it 10 EV to typically 1 GeV, 10 GeV, the wide range. So when we consider this kind of energy range, huge energy, we go to in science, particularly physics or mathematics, we go to log scale. Chemistry also, all basic sciences. So this is a log scale. So distance here and same distance here is probably 10,000 times. So we have to switch our brain that way. But it is very important if we want to give the whole spectrum of energy, how it behaves in a system. So you want to give a flavor. We'll see when ions are going to typically 1 MeV, mega electron volt. Energy is EV in ion beam is due to fact it moves in a velocity which gives the energy to that, and Q is the charge. Q into the voltage gives the EV. The EV is typically, you can convert to all energies, but this is the most popular energy in the low energy, medium energy, high energy mix and with ion beam. So if we go to this whole energy lens, we will see as we impart more and more energy, this is the energy scale. Energy loss, how much energy is transferred to the system, accordingly varies. So if I go to typically 10 to the minus 1 MeV, means 100 keV around, then this kind of ion matter system, silver beam in gallium arsenide, one of the case, but it varies from species to species. So every species we have to put it. So it actually first it comes peaks around hundreds of keV in the low energy beam. This when implant it, we implant ions to tens of keV to hundreds of keV. But when we go further in mega electron volt, it peaks around this. But this peak spread is much higher than this peak, because this is a log scale. It is typically 100 times smaller. It is squeezed. So this peak actually, if we put a linear scale, it goes on for some time and fall. What is the physics behind it? Is that when we are giving kV energy, the electrons, if we call semi-empirical, quantum mechanical process, electrons, if we consider electron moves around an atom, a simple model, the electron has a certain velocity. It is called Bohr velocity. So until Bohr velocity, if this ion beam, when it is keV, tens of keV, hundreds of keV, its velocity is so low, electrons moves quite a few times, the electron cannot feel it. It looks like a whole atom looks like a solid ball in low energy. When it goes to higher energy, slowly increases, ion's energy increases to velocity of electron. So electron is moving, ion is moving. If it is nearly same velocity, so it actually there is electrostatic force imparted to the electron by the moving ion, which are given by accelerator. So actually, as it comes to closer to electron velocity, actually maximum energy gets transferred. By the force into time duration gives the impulse. So, the simple physics wise. So actually it starts peaking at very high energy. It is tens of eV for proton light ions to hundreds of MeV for heavy ion, like gold, silver. Why we choose different this? We have an accelerator nowadays. Modern some of the ion accelerators having are capable of giving ion from proton to uranium, whole periodic table. So one choose the ion, how much energy one wants to transfer accordingly. So I will show one case also, track spinning or something like that. So this is the way it works. Basic science, if we understand, then we understand how to use case by case as the problem. So this is the simple language quickly which I can explain. And if some questions comes, I'll come back again later.
SN is
SN we call actually nuclear energy law. Okay. So this is coming from history. Earlier nucleus the Atomic Energy Commission, nuclear energy actually. So atom used to be earlier considered as nuclear. So Bethe board, when they came with this terminology, that time they gave initial classical picture of that. I told semi-classical kind of thing. Then once later actually it is refined with all quantum mechanical corrections, all those things. But term remain nuclear. Actually it is atomic displacement. So it is so scientifically talking, it is elastic collision. And when electrons are knocked out, electrons are disturbed, then it becomes inelastic. So this is known as elastic collision, it is non-elastic. I'm sorry I didn't put the AC is electronic. So this is the terminology is maintained historically. Nuclear energy loss, electronic energy loss. But physics-wise, it is elastic process. When in low energy it is hitting, we have scattering theory. We study those things. Typically low energy. When high energy it goes, it actually disturbs the electronic system. So I'll take a case also, electronic excitation. Very good question. And this is the curve actually mostly used in detector development or nuclear physics. This is called Bragg curve. So if I actually, this is the same curve, slightly one has to orient a bit with that. If I put ion beam at this energy, suppose. So this energy to this zero energy, it will go a long way. So this will be like that. This peaking will be at the end of this, from the surface on this side, curve has to be in. If I put the ion beam at this energy, it will go a long distance with this energy, then it will pick up and fall quickly. So this curve is same curve is actually used on nuclear physics. This is a curve actually maximum used in hadron therapy. Now it is a big societal impact on beam is hadron therapy. And we already have in Chennai, is doing even for abroad, patients are coming, or developed countries also. And TMC, we will have a Zhajjar also. It will proliferate. Actually, there are quite a few, there are few lakhs treatments. It cost also is coming down due to the development of this technology. India, another 10 years, it will be full of. But today's talk, I am not going into that. That will take in another direction and it will take a lot of time. So,
elastic scattering, there will be also some emission of some radiation. And
in elastic collision, generally radiation is not expected. Thermal process will be there, thermal excitation. But thermal also you can say radiation in that's lower electromagnetic side. But in elastic collision, you told, huh?
the elastic.
In elastic, there will be big radiation. Even nuclear radiation, sometimes if it goes to Coulomb barrier, there is, Coulomb, finally, actually, whole charge is at the nucleus, the positive charge. Ion goes, that is also typically positive. So positive to positive, there will be repulsion. If it goes within 10 to a minus 12, minus 13 centimeter like that, or uh, femtometer, then that kind of breakup will be there, nuclear energy. But it actually gives photon, lot of photon and KeV photons also. So there will be radiation. And in elastic, it will be more thermal process. Mostly we use low energy for, but high energy is being used in lot of cases, nationally, internationally also, for even produce energy. It does another thing which I am not covering. This is transmeric element which we need. So there is a accelerator-driven subcritical system. Accelerator drives the reactor. The reactor cannot have a big accident, and plus long-lived isotopes are reduced life. But I'm not covering there. These are done in that range. So typically, which I told, typically if I give in terms of number, typically 1 second per nanosecond, 1 centimeter per nanosecond velocity when it goes to match of the, so that kind of thing takes typically 10 to the minus 17 second, minus 16 to 17 second to cross the one single atom. If you look in the solid each atom separately, but you know, phononic, this process comes at 10 to the minus 12, minus 13 second maximum. So there is a electron phonon coupling. It comes to the lattice to that process, and this time is taken by this. Even 10 to the minus 12 seconds, as you know, is a very fast process. But this gives a very fast annealing. Also, a lot of annealing cases they are used. And this is one of the modern this implanters where we use ECR, electron cyclotron ion source. We are one of the few centers where we introduced very beginning, which ECR also technology developed, the ion source technology. I'll just touch upon this. This is in IUSC. We built on a high voltage 400 kV platform, and giving them electron cyclotron ion source, unlike EIG source, typically we use other source. At current increases or it works for certain time, you have to change the cathode. Oscillate means negative ion source. Here actually it is trapped in a plasma confined in a region. It is continuous. And these are the type of ion used for add-on therapy or kind of activities. So this is one of the.
So it's a particular type of ions or
any gas, any on the solid, you can sputter them and put in gas. Then it becomes plasma, and the radial and axial confinement is done. So it remains in the space. It doesn't touch anything. So once you have this, it is for 6 months, 1 year also, it will not change. There are some of the activities where they cannot afford to have 1% change in the beam. So these are tested that way. Only if operator does something or some power related issues come. But we generally these are put on UPS for sophisticated use, and it doesn't change. And this is another thing is that now why a lot of short it, but you know, across the sample, charge getting older takes time. So another way is that put electron plug on this electron source. That is also typically used to be done. So nowadays, negative ion sources generally use this kind of sensitive cases. So these are the new systems are coming. This is the beamline for experiment. And as focused ion beam, probably now it is in textbook also. This is another type of beam is coming. A lot of time I find it is used for even cutting the sample for TEM and all those things. But if you are very creative and have enough time, it needs quite a few years to expertise and really make that. You can make the solid a certain size of a style, but one has to optimize all the parameters. But typically here beam comes within few nanometer. Earlier micro beams used to be there. Nowadays nanometers beams are, and these are now available off the shelf. Like TEM, SEM, we can just buy this from market. Some of the things you have to make because it is not available. Or you have to pay huge for development, like a electron or something. But here, actually, these are available. But it came from the development side effects of the development of accelerators. And these are the, actually, when we see the ion beam, when it goes, we see accelerator, those things, you have to treat it. We like a photon beam also, you have to focus it again and again. So here also it is focusing quadruple lenses and there are optical. It is called beam optics. Like photon optics, it is beam optics. And each one has to learn those things physics wise. So, but we had a lot of courses on that. And this is a new kind of ion source are coming, single ion implantation, single ion doping, all those things. It developed in this thing in SARE. SARE has a very ion beam center, totally dedicated to ion beam, all kinds of accelerators and implanters. They developed it, is now commercially also, some companies are selling it. So now with this quantum initiative, quantum mission, this it started from your nano mission, but it is getting popular. So it is particularly useful for where you want to have a single atom. It can, like piezo, you can position atom within few angstrom or angstrom level. So you can have your position and dope it. So this is a modern development. Now coming back to our system. This is locally single atom controlling atom. And typically it is hundreds of ions. Before that controlling we can stop. It stops it. And there are another thing also. There are some places where high energy ion also when going. There is a detector. It detects an ion falling and energy beam current is reduced drastically and you can bring the next one. But these are all done by piezo control, like STM, FM we are doing. Piezo is piezo control is quite easy nowadays. And all these control circuits, all these things are available. Earlier we used to build it. And even JP Singh developed a vacuum STM when he was doing PhD. And got a feeling, piezo. And we knew physics wise, we knew. But actually, a lot of technology came. Knowing the physics also, always we cannot use simultaneous development other things, like good amplifiers with low noise amplifiers and called instrumentation amplifier. Then no noise voltage control. The piezo has to be within extra movement, one has to control those things. So there are many finer issues, but world is developing that way. Yeah.
For solid metal ions, you said that first we form in the vapor form, in the gaseous form that solid. So how you basically make them vapor form by doing sputtering or
Sputtering. There is one thing is that we actually make wire and we sputtered by actually that plasma. So we put some background gas, nitrogen or argon, and it actually formed that plasma confine. And then we put a voltage across, it sputters and that gas comes.
how you separate them like argon?
That is what I told magnet.
By
There can be hundreds of background mass, so we have a filter, strong filter. Electrostatic magnet also has some filter, all kind of filtering is there. That is, I'm not going into that, those are coming under pure accelerator technology or science and technology. But I am giving some flavor what are there, because each one goes in long route. Actually, there are whole accelerator program also in master degree in accelerator physics, actual science, or BS degree. So India, we are actually certain labs, we are having accelerator programs also. So we have training school controlling those. Coming back to this is one of the modern accelerators. We have two tandem accelerators. This is an offshoot of Van de Graaff. Van de Graaff accelerators, what used to be there used to be a PIG source. And penning discharge, you can see as higher charge state goes, this number of particles having higher charge state falls down. So typically you get few plus, suppose I take nitrogen. Nitrogen 1+, 2+ will be maximum, 3+ will fall, 4+ will fall like anything. because partition function goes down as you go higher charge state, minus delta E by kT. So e to the power, so my delta E is 4 times bigger than your ionizing to first state, removing 1 electron. 2 electron removal becomes minus delta E by kT lower. So after a few electrons removal, it is practically impossible. So this here it is taken, this instead of terminal having an ion source, it is taken outside in the world. So negative ion has to be produced. So first source of sputtering negative ion is needed. This tandem concept started building late 60s, 70s, it got matured. And by the time we took up 18, new technology came like ceramic, tubes, compressed geometry. There are many things. I'll come to it one by one. But here, instead of terminal, ion source is taken in the outside on the ion source room. And this same voltage is used twice. So that is why tandem name came. And pellet toss is one thing where by pellets we have started giving charge. After 10 megavolt onwards, with lot of difficulty it went to 14, 15. Afterwards it could not cross. The pellets came, the insulation, and then pellets, one by pellet, taken by insulation. I will show it. And you can put up to 25 megavolt. Oak Ridge has shown initially. They have they have the largest tandem, not actually 20 plus. Ours is one of the 5 large tandem. So we cross 15 megawatt typically the series. The initially plan was 18 megawatt, but we had to come down due to this airport nearby. They have a runway that time planned. They have planned for next 20 years, 30 years, 25, 30 years down the line. Now it has come. So that so they didn't put this. They restricted the Qutub Minar height. We had to go down, and we came down to 15 15 units, but with compressed geometry we made 16 megawatt. We tested up to 17 megawatt, but 16 megawatt with beam. We ran some experiment. Mostly we run at below 15 megawatt. So this technology developed side by side. There are special tubes came, all metal. And in fact, we had a Medigraph accelerator in BARC, which was converted to this kind of, with this kind of tubes and pellets, converted to modern accelerator. And it is working quite well. But we actually, when we did few things, new things, which were not there in early any tandem. Actually, always when we do something, we do differently. We see some paper, we think ourselves, we have new ideas, we introduce in it. So one thing is that till nobody could defeat us in offset quadruple, a triplet in the terminal. So we can separate the charge here. 4, 5 centers planned, but we did it, and it is working. And 4, 5 like in Israel, they have a big one. In Yale also they are tied. In Italy, one group. But this is one thing. It actually quadrupole focuses. If we slightly offset them, we can use that focusing plus dispersing charge state. So there are some Russian people give the theory. We put into practice. And then earthquake protection, there is earthquake zone. In case of earthquake, actually 4, 5 accelerators destroyed. Latest one is Suguba, the last earthquake. That there was not only a big accident, reactor which people know popularly, but the Sukuda accelerator tandem. And since I learned from them that this kind of protection is possible. In Delhi, we have put fired once the 6.5 Richter scale accelerator held because it's a huge investment. So totally it goes down. Sukuba was pathetic if you see. Even they have money, they get another one on there. But
What is that?
energy spread, this is one good question, very important. This kind of this tandem energy spread is 200 kV, 200 MeV, 250 MeV. It will be 10 kV like that. So this is very precise energy, unlike most of the cyclotron. Energy spread is quite high.
So one very naive question. So when you look at the or when you want to isolate those ions, you want to have only one single charge state, or you want to have multiple
Now, once you know if we put a this magnetic dipole, so it will take this one charge state for a particular mass. But beauty is that with negative ion source, still we put because other negative can come. They are molecular isotopes or something. Negative ion source till now quantum mechanics also you can show it. More than one electron cannot be added to any atom. Okay, it is not stable. It cannot have a stable configuration. It is called electron affinity based on the because you to tap something you need the potential well. How sharp is the well, how depth is the well that defines how much time it. The different species stay negative for certain time. So it is negative ion source only one we add on electron. I have not gone to ion source part because that will take another direction. Important thing that we use cesium. Cesium, rubidium, they are electron giver. We attach an electron to that thing. And that stays for few microsecond to millisecond. Before that, it comes to the terminal with a 15 MeV or 16 mega electron volt, very fast. And then this terminal is steep and it becomes large number of charge state, which we separate here. What energy we need? Terminal potential multiplied by that plus one charge into this terminal potential. So 15 megawatt. So 15 this MB or 60 MB is the terminal potential. When it comes with few hundreds of keV. The ion source is ion source is like an implanter kind of thing. As to get that velocity, but once it enters, it comes to here 16 mega electron volts, tremendous square. So we put some gas or foil, it passed through this, electrons are removed from the ions. Typically, let us take silicon. Typically, 10 electrons are removed. So it becomes silicon 10 plus. 10 plus into 16. So this is the next portion actually gives huge energy, hundreds of MeV. And then 11 plus will be there, 8 plus, 9 plus, all kind of thing will be there. This magnet, lower magnet is a huge magnet, nearly 2 millimeter the radius. This magnet actually throws other charged out. The particular energy we choose here and put in different beamline. This is a very simple schematic I have put, the detail not. And compressed geometry tube developed that time. And we are the first accelerator, a lot of accelerator converted. We planned with compressed geometry. It was around 85, 86 that started when PC and all those things started coming in the market. So
there is one question.
So,
yes.
This accelerator, we have a very broad range of energy variation,
Mm.
AEV to MEV.
Mhm.
And there is also, because with accelerators, ions are accelerated, so X-ray beam and gamma, some radiations are also emitted. So these radiations are destroyed, or is it any way that we can focus this X-ray radiation for doing other measurement like RPS?
Okay.
Because
Probably some microphone is there for the other people who are online. They will not know that what you are asking. But anyway, before you go further, since they are randomly put that this radiations are plenty of radiation. So if you see the building, in fact, this steel big tank also is made on the site. This kind of tank cannot be moved. Nowadays, maybe high power, some with defense, there may be some helicopter nowadays we have. At that point of time, we saw from helicopter also bringing it up. It is easy to do and component science. So we put a laser beam through it, and multiple detector made a tank, and this thing also made by slit forming. Now the not common technology. Actually, it is done by Sapurji Palanji with Tata Consultancy. Actually, slit forming based on radiation, we increase and decrease the thickness. As it comes down, actually it produces more and more, not only that X-ray radiation, high energy X-ray, it produces nuclear radiation also. So, and since these are not intended, we stop them from coming.
my question is it any way that we can use that generated X-ray for the?
I got the point, but since it is randomly generated, it will not be useful. In science, we want something where I have control. If something comes out of control and not as per my liking, I'll stop it. Parasitic radiation is called. And since this accelerator produce all kind of ions, so it is someday it will have this kind of X-ray, the next day it will be different kind of X-ray, different kind of gamma. So people need something they will not get next day. You understand? So actually, this I didn't go into it. We have radiation shielding also. We have health physicists. We had to do the detailed. For Delhi, it is very political. So he had to do very much. Even after doing all those things, before starting also, he has a lot of problem from PM, all kind of questions for people, person could raise. So there are many issues. But the biggest thing when we are there, our children are exposed, we are exposed, we cannot take any chance with us. We cannot kill us. Others are better. So he did all those things. And then the ultimate satisfaction, because system doesn't work that way. I tell I have calculated, it's fine with me, nobody will listen. So we have put hardware, all interlock, whole machine will be stopped if radiation level anywhere goes up. So we have neutron detector, gamma detector, all those all throughout the building, everywhere, area monitor. And they are all interlocked. Even doors are also intelligent, door will not open. By chance, some students did also. Funny thing they do it is expected also. We don't mind, but it whole accelerator shut down, and big system actually shut down. Bringing back is tough. Once even accelerator was flooded with air, so all kind of things happen. But we have now. Then we learn next step and put it. We put area, and nowadays cameras are also is cheap, continuously monitoring. But all the doors, actually, if it opens, there is a magnetic sensor or those things, immediately shut down. But still, it is shut down means, and again you have to restart the process. So, but no radiation actually can take place. There is a AERB. India, there was no till now big any accident. Our Department of Atomic Energy is very clear. There is a separate radiation regulation board, and they come and they satisfy themselves. First, they see the calculation when we can go ahead. All details calculation thoroughly we have to give, and later area monitoring, all those things, hardware connected, seen before giving the user beam, all those things are done. Until now, there was no accident. In fact, some of the radiations of IIT camp, Delhi also, were kept here and there. We took it, our hot room. So we have a Professor B.R. Mehta's time. So he contacted me because you are not supposed to have any radiation source anywhere. Delhi University case, you know, even the person at the age of 80 was pulled up and he was jailed. So there, this cannot be actually. Sometimes education institute sometimes try to lose income, but they here we are under regulation. So no thing. And then your main question is very important question. You ask a good question. I would say there is parasitic radiation. So our building stops it. Walls are designed accordingly. Even beam hall is very beam hall ceiling is 1.2 meter thick. We don't want birds also to get radiation while going around. So we have done all those things. And it was a long process initially. But this project is one of the project finished before 5 years was given before time. So we had our founder director, Professor Patro, worked with Meghna Shah, who made the first accelerator cyclotron in Calcutta. So, and Bidin actually that time was scientific advisor. He was the other student of Professor Meghna Shah. So he also was in scientific advisory committee. And outside, this is outside DAE system in academic system like university. IIT also a part of university in the bigger sense. So all this system, this is the first accelerator. It is common in the USA, but in France particularly, CNRS comes outside CA. CA accelerators, separate CNRS is there. So similar line during the Prime Minister of Indira Gandhi, this was sanctioned, and we came in reasonable time. But we learned a lot of things going to VRC, TFR, electron. He started before us. I'll show it. This is 14 UD electron. There are quite a few. What electron is the first one, or maybe last one, big electron in the world, because we had that aviation related issue. So that we had to do a lot of beam optics to go away from the general rule, and could do due to Professor Patro, and he was working together. And I also come from field of laser. So optics is in my blood. I was in IIT Kanpur, designed also. For our PhD, we used to design. We didn't have that kind of dollar in 70s. Okay, this is accelerating to I was telling. This technology is a beautiful technology. Earlier, all accelerators used to have this insulator plus glass, bonded by any bond. Any bonding material has a life. It dictates. If you put a envelope also, after some time it opens up. After 10 years, 15 years. So they used to be changed. So these are bonded like that ceramic N2O3, very pure ceramic. And then this metal, typically most of the time titanium is used. Our accelerator all titanium, or it doesn't have money, somebody aluminum is used. They're bonded by diffusion technique, solid state diffusion. It diffuses across the metal to ceramics. And so this is the new kind of accelerator tubes designed there, and he patented. So now technology is well known, and at very high temperature, high vacuum, it is slowly pushed across, and there is no organic, there is no glue, nothing is there. So it can go to ultra high vacuum also, to -10, -11 also it is tested. So because high energy, highly charged particles move faster. So these are the technology, and this is the technology I was telling, gave us 20 plus megavolt. This pellets are like that. There is an inductor. It induces a charge. The neutral pellet comes and separated by a nylon, very strong nylon link. And when each pellet comes, actually it becomes positive charge induced, negative charge further away, negative charge gets grounded. Okay. And by the time it gets grounded, positive charge also is spread across it. By that, it is dynamically, velocity is adjusted in such a way that by the time negative charge gets grounded, positive charge cannot touch the ground. By the time it is removed. So with positive charge it goes, and this is the terminal of the pantograph or tandem. Pantographs are also replaced by this nowadays. So this comes there and charges it. And it is a terminal is a Faraday cup, a Faraday body. In a Faraday, any charge put inside, it comes from the outside uniformly. So, single potential it can have. So this is a new technology developed side by side. It helps us to go this kind of megawatt. Now let us, if some question is there, we'll come later to that. And these are the way the ceramic, metal to ceramic tubes are there. Each one typically for us takes to 1.17, 1.15 megawatt. They are actually initially designed for 1 megawatt each. These are called units in the system. They are building block of the accelerators. And then, as I told, offset quadrupole, we put in the terminal. This is a new design, and we totally did the beam optics, and we are having our finger crossed. But when whole system started working, we took some time. With mathematics, give some value slightly, we have to tune across. But nowadays, it is being done like anything. We can, when we go through a steeper, it has all charge distribution. We take a particular charge we can take. When superconic liner came, it becomes very useful for us. This is a peloton TFR. They started before us and finished also a bit before us. This is a 14 UD peloton, and they have similar program. Mostly there is a big spread across, but DAE labs initially, now they are taking some of the universities also, and it is also running quite well. So these are big two modern tandem accelerators. There are other accelerators also, like, let me see. When accelerators was building side by side, actually we have to go with time. So RF superconductivity started developing. RF superconductivity is different from DC super. Mostly in our textbook we teach DC superconductivity. But DC superconductivity is that anyway, superconducting, it doesn't follow Ohm's law, as you know. It is a coherent movement of Cooper pair. But DC superconducting beauty is that if there is a percolation path, there is some defect, it takes another path and goes through it. Like where we are putting current, if we dent something, it will pass. RF actually it penetrates up to this London penetration depth from the surface. So your surface should be perfect. defect free. So these surfaces are prepared in high vacuum, and all welding, all kind of forming is done in high vacuum using electron beam welding. TIG welding, all those kind of welding which we put USB cannot be used there. So, this TFR actually they went for this accelerator using copper coated by your lead. And IUSC actually that point of time we started a bit later, and niobium superconductivity started coming, and formula this Argon National Lab was there. We actually collaborated with them. Initially made few, then totally this technology we developed in IUSC. We made niobium. Difference between lead and niobium is that this superconductivity temperature TC also goes 2 degree higher, and at TC JC is 0. So typically we put at helium 4.2 Kelvin. So further is the TC, we get more JC, so more field for the same expenditure of power, electricity bill, and all those things. Same helium. So we actually started. So the difference between this is a quadruple, and how this accelerates further. Actually, once we started giving few hundred MeV, people are for particular nuclear physics and some of the black curve which I have shown, actually 200, 300 keV, actually your elastic process falls down. So your AC becomes much higher than SN. So effects are purely due to AC effect. There are some region where AC, SN both are there with that curve which I showed. So if you remember. So this is the one development, it is called booster. This is the process all over the world started going that time. We, particularly New York State University, even JARI, Japan Atomic Energy Research Institute, Padova in Italy, in Germany, all over developed countries. And India, one thing is that if you really look at it, what developed countries does, we do nearby closely, but we are a bit behind. It is not, we don't think about it. And or sometimes it depends on how much funding also we get. CERN takes billions of dollars. For us to one accelerator center putting few billions are not easy. So we become part of them. We in CERN accelerator also contributed in a big way. I'll show one of them, the accelerator coming familiar, how we are contributing. So this is a good program which TFR and we started doing. And how it works actually, we textbook we see linear accelerator. As velocity increases, uh, tube increases size. But where you will go, you cannot go to infinity. Here size remains same. As velocity increases, there is a electronic drifting, gives a delay, and put the next ion. There is 10 of them there. First one increase the energy, velocity increase. Next one, when it gives some signal that you come to this potential, accelerating potential lower. And how it accelerates? Suppose positive ion is coming with certain 100 MeV. When it is there, this terminal becomes negative. So there is a RF frequency. These are called cavities. It becomes positive, negative continuously. But when positive ion comes, it becomes negative. By the time it passes through this, it becomes positive. So it pulls the beam ion and push it through it. So this is a new technology started developing in the end of last century, beginning of this century.
It is similar to cyclotron X. They are also here. This
Cyclotron D actually does this. You're right. By the time it goes across, but cyclotron here actually thing is that cyclotron once you design, you cannot do anything later. You cannot make a bigger one, all those things. So you have to design and forget. And then variable energy now this organic cyclotron, I show one slide. They are actually they can mass wise also they can change a bit. But beauty of this accelerator, as you get money, you put another module, another module. You can go to practically infinity, provided you have space and keep getting money. So whatever we could get, we have many module. So this is the best way today, actually, till today. With sun also, 27 kilometers, you see, there are many this kind of acceleration section. And then bending magnet. More than 1,000. There is a 27 kilometers, two countries below the Switzerland from France. Main entry from Geneva. And it is typically nearly 20 meters down below Earth. to take care of this radiation and all those things. And some where detectors have been 30, 40 kilometer down. So that we are also associate member of this sun.
So these quadruple magnets, these are also fabricated here.
Initially we bought, but now fabricated. Now conflict plan, everything we do. A particle machining center, we have so many CNCs. We have a very good facility. But we had first electron beam system in the country, outside ISRO, and sophisticated. Now we have few in the country.
Dr. Pankaj.
Yes, Kanjilal speaking.
Yeah, no, actually, I think Dr. Pankaj is also sitting near the mic. So some crosstalk is we are able to hear.
Yes.
Yeah. Can you hear us?
So
yeah.
No, actually with Dr.
Yes.
Yeah. So I could hear Dr. Pankaj also discussing with somebody. So that's why I think you maybe switch off or go away a little bit from the mic.
Bit far. Okay, maybe.
Okay.
Maybe. You can put it off.
Yeah.
Or mobile maybe some connectivity. Okay, can you hear the questions being asked? Probably it is difficult, huh?
Yeah, that I'm good. Yeah, but then other discussions are also coming in the background like that.
Putting it off. Okay.
Yeah. Okay. Yeah.
Okay. Now it is fine. Okay. So this is the
it is fine. Yeah.
Together, one by one modules are added. Huh? Similarly, IUAC, as we told, with Navium resonator, similar kind, not of aluminum, this copper coated by lead. Actually, coating technology, electroforming, electropolishing was very much there. But we went for that. We had some problem. And biggest problem was that after this bomb blast, we are in entity mode and all kind of thing. For us, also movement was restricted. Visa was not given. Lot of things we went to. But we developed the technology. Whenever we go, we get effect, we take another path. But science is, we know practically science may be as good, except very few. I tell you here one point. In top accelerators also, if you see even big discovery like this gravitation wave and even Higgs, all those things, or all kind of technology. If you top few people, you'll find some Indian there. But typically Nobel Prize is given to three. It doesn't come by 5, 6 onwards. So, but we are there. Everywhere we are there. Even for your information, I say one thing. Pichai, he did his work with iron implantation with Indira Gandhi and all the things in Banerjee in IIT, Kharagpur. His thesis is there in the internet, you can see. But what happens? We start learning, our people goes everywhere and we have idea. And as we get money or support, if we are intelligent, we can make it, anything. So I'll show once. Formula first two modules is ours. So anyway, coming back to this is the kind of module we have instead of 4, 8 of them in each module. And we went side by side in this. And we have a lot of collaboration and lot of interaction. And TFR, the BRC Peloton and LINAC program helped us a lot because first they are always a bit started before us. So we could learn many things and learn from the difficulties also. And then we had one thing, we are in general academics field. So we can quickly have a collaboration with somebody. And this is very important in science. If somebody has done something, it's better to talk, not rediscover the wheel or something. But anyway, it depends on the different thing policy. Like see, future synchrotron, if you go to our this internet site, we have vision, mega science vision 2035. This all these documents are there, PDF files in the office of the PSA, Principal Scientific Advisor. So you can download also for 35. we are putting based on this. So the future synchrotron, future something, when we do, somebody has put a lot of money, they have learned something. Learning, they you like book, who has written, doesn't matter. I did it, I can learn it. So similarly, technology, and talk it clearly, scientists, engineers, it needs a lot of engineers. We had a lot of good engineers from IIT Delhi also, air engineer, different IIT. So we worked together and made it possible. So nothing is impossible. That is my message to younger generation. This is a control system, and I will not talk much about this, but everything is controlled by from here through the computer. And as computer changed, we initially started when we started, PC started coming the market. PC, PC PC, then uh, PC80, then modern PC came. So we started with Algol and then C, then other language, over time with different language. So, but what we did, we mapped the whole accelerator to the control rooms. Our register each is looking for equipment. So beauty is that a scientist can run it, because earlier accelerator, a lot of time you need a lot of operators. They know what knob to move, what knob to do. But scientist knows I have to touch the control this ion source now. I have to tune. I have to change the gas. I have to change the velocity. I have to change magnetic field. So that they know, but they don't know what knob does it. So they actually call the page and see the page accordingly. They can do. They put their things in the register. Register points to the device, and the device, if you put it on, if it goes off, because device is dead, it shows back from the reading that it is not taken my command. The command is given and command is read from there. So if I put a from here something on, I think it is on, I have to check, cross check. So these are all implemented. Those are the ideas coming, and we had our complete control system made here. We didn't. They some of the suggestion was there. DAE used to give PDP series. So we didn't go into this. We went to Indian PC made by Wipro that time. Was good. Started with that. And then today it was developed in the modern, everything is controlled from there. All over, this is spread over 200 meters around. And this is another accelerators. Now it is quite operational in variable energy cyclotron. This is a superconducting cyclotron. This is a very modern accelerators and made mostly indigenously, and winding, all those things are done indigenous. And this is going to have a big impact in nuclear physics community and material science, high energy material scientists. Now coming back to how much time I. Okay. So I will come to another thing. The accelerator being used for other field also, associate field, and art science and physics as well. This means geophysics, geoscience, art science, the field. So there is a term from accelerator mass spectrometry. Physics wise, it is, if I see, long-lived isotopes are stable typically. They are living for a long time. And there are isotopes which are very, decay time is quite high. So if we have, suppose any ion, for example, let me take one, carbon. There are many isotopes I have shown here. Mostly carbon, beryllium, aluminum we are doing here. But we have done chlorine and all those things. Pankaj is from the field. He did his PhD also in this field and is internationally well known in this field now. So residue isotopes, let us make it shorter to go with carbon, and then beryllium, aluminum will be similar. Physics is similar, only process will be slightly different. So half-life with 10 to the 3 to 10 to the 10 times, 10 to the 8, 10, like that, we can take in. When the tectonic movement we study, like how Eurasian plane was hit. So it has happened about near billion years. So we have to go hundreds of million. We have to go very high light species. But if we want to map the Earth for last 70,000 years, 50,000 years, what has happened, glaciology, how this even this your river bed, how it is changed, or lakes, how they are changing, all kind of this this earth science related issue, geology related issue, or dating of our artifacts also. Actually, carbon dating is nowadays, dating means people understand, so let us talk about carbon. This is a field where we didn't have much presence except doing using our existing accelerator. We dedicated one tandem to this, and this is one of the only one tandem having completely means damping power, because we have this is a standard sample varied to different labs. But let us go to the science of it, how it is done. Okay. Probably I'll come to it later. Let me say, before that, let me tell one point which I was mentioning, which has got in. These are the spoke cavity we fabricated of Hamin National Lab. They have a PIP too, if you can go website, future accelerator coming up. Very high intensity proton, which we get. We have our spallation in future. And as I mentioned, accelerator driven subcritical system will need this kind of structure. These are called, I took quarter wave resonator I showed, spoke resonators. They are needed high intensity proton, milliamperes of current proton to be accelerated. And this was we taken as the order. These naviums were given after, this is after our this sanction, all those kind of period. Then again it was a reopened collaboration. All the scientists are always keep collaborating, but government wise. So our Fermi lab approached us, and then we made these two resonator. It is at Fermi National Lab, and they have been performance wise. They tested. They have given to many Japan, various places. The magenta is our result. This line. So they actually expecting better than these cards. So we are far above that, and it continued accelerating to more than uh, 18 megavolt per meter. Requirement was around 14, 15. So, and then they have put in the first two modules in the main first entrance accelerator in Fermi lab. It has been running there. But so actually our idea is that we can deliver, like I have not come to Sun. Sun also deliver many magnet characters, many things. This latest one, recent one, is Fermi lab we have delivered. Before going to AMS, let me go in some of the characterization. There are a lot of students here to condensed matter physics, material science. So I'll say, all the other four back scattering you have studied in a book. What is the important issue? There is a nucleus which can scatter back, because atom most of the thing are hollow. And this used in by using a tandem. We are only one of the two labs in the world having three tandem in the campus. So this is one of the tandem is dedicated to this kind of back scattering. So I will show what is the beauty of that. That's suppose thin film you make, like this gold film on silicon. So a gold film thickness you can measure from there how much thick, how it is, and silicon without perturbing anything. Film remain as it is, non-destructive. And but more beautiful thing is that this is on the surface. You can take a stylus, you can put, or you can go to Sims and do it. See, okay, one sample gets destroyed, doesn't matter. But if you want to characterize a sample and same sample you measure, same thing, then you have to come to non-destructive testing. So if you are multi-layer, like platinum, cobalt, platinum layer, so you will see that nicely this you will have the signal cobalt here, two platinum layers. Intensity wise also you will know, and on the silicon. So this is done within a very short time, and we have a tandem. More importantly, suppose this is non-destructive. So multi-layer, when you put many layers, 10, 12, you want to know this. Even from abroad also samples comes for this. And it is like many layers, like 5 layers. So you can see 5 layers coming like this. So what is there? Actually, same Rutherford backscattering. Only thing is that there alpha, which was coming naturally, was being used where it can go like that. Here we can produce the ion beam, which we need, the energy we need up to what depth we do, and do the characterization. But even better for people who work with pure system, this is the system. This is a tandem accelerators. This doesn't need that big 16 megavolt tandem. It is typically 1.7 megavolt per electron is used, and this is the chamber in which we can do this channeling. So actually, it looks like that. These samples are they are detector and beam, but we have a goniometer. We can align the sample to the axis. You know, crystals, if you have 100, 111, or different axis you can look. So you can look inside the crystal. If you can look to the angle, all atoms will be aligned to line. So you'll see a lot of lines and in between a hollow space. And interstitials can sit there. So what we can do? We can do the channeling. And this is very strong practice. It needs time also. You have to slowly align, come to the one of the crystal axis. Suppose one axis 100 you cannot see. It is sitting in another, getting shaded. Another axis you put 111 and then see them. So whether if you make a pure crystal, then you would like to know what kind of thing interstitials are having. Like a lot of time when we envy a lot of nitrogen are present there, which are not controlled by put. So they are random centers. So similarly, a random uh, disturbance can clearly seen by channeling. Rather for scattering, main important science is swing channeling. When you actually you can make a film, even thousand sites are gone. If you take an XRD, it will have same pattern because you are seeing case space. But if you take an STM, you will see some atoms are missing because you are saying direct space. Directly you are having tunneling current there. But case space will not know, actually intensity falls down, but mostly it is normalized or so much is not felt. So what I mean to case space is good, like we see in TM. But when we see in STM, actually this gives direct. And you can see density of states also. You can have tunneling spectroscopy. So wrong atoms are sitting also, you can understand. So similarly, channeling is one of the things it goes inside. This is I thought I'll cover before that going to this thing. The channel actually done long crystals, very nice channeling can be done. So this channeling, if it goes to, I have seen system wise, like this, if it is backscattered, how backscattered can get transformed when it is channeled. Because it is going across this, no other for backscattering falls down. So if you see RBS spectra, you will see big fall in the spectra when it channels through. And then atoms are there, it will give the peak accordingly. So now let me go to this because I wanted to finish accelerator part a bit. This thing we are doing glaciology, all kind of work, and more than 100 research groups are using the facility. We didn't have it. Our sample is to go abroad earlier, and it goes through a lot of payment also issues are there. Huge payments is to go. Now we developed in the country this facility. It is called accelerator mass spectrometry. Why it is so special? Well, there are same there's mass spectrometry, astral mass spectrometry. There are all kind ICP-MS. There are thousands of mass spectrometers. What is beauty is that it comes from basic sciences, is that these are the some of the radioisotopes which are cosmogenic were created. So when some system dies, it doesn't take any, like carbon, it no more takes carbon. Then what time actually some tree dies, then carbon 12 actually long life lived isotope, nothing happens. Carbon 14 every 5,000 years gets half. So if you can the carbon 14 to carbon 12 ratio, you can say when it died, when this happened. That is how this is done. But it has to be done to that accuracy. Carbon 14 is very small trace element in carbon. So you have to have a technique. It cannot be done with simple mass spectrometer. It has to be done accelerator mass spectrometry. Here I will show this your efficiency, sensitivity goes by factor of million nearly. So that million is a big term. So you can have very tiny space element in this. So this carbon is very popular That is why carbon. And Pankaj wanted me cover more, but I saw I have to do a certain time. People cannot sit for so to give some message as per my title. So carbon 12, carbon 13, carbon 14, these are the number of atoms. So you can see 10 to the 12, you have to 22, you have to measure 10 to the 10. So you can understand how trace it is, trace element it is. But it has to be done by accurate. Carbon 13 also having less lifetime, so it is ratio. But it is also measured. Both are measured to have systematics also in the system. So the carbon 13, 5,730 years of lifetime. I will show some simple example how it works. So, and this carbon 14, how it goes to nitrogen by decay after this lifetime. This is the process by which its ratio given. So we have actually this tandem machine. We have these two types of ion source. One holds 134 samples, 140 samples, depending on the case. We can put it. What is the beauty of this is that negative ion carbon can be made, so nitrogen 14 cannot disturb it. Carbon 12, two hydrogen together also molecule becomes. Actually, all this mass spectrometry, biggest contamination is molecular. All kind of combination molecules come through it. So there is a steeper, as I told in the tandem, there is a steeper here. Actually, it breaks all kind of, no molecule can come through a steeper. So molecular contamination totally gone. Atomic isobaric contamination also done by this EB, this system, electrostatic plus magnetic dispersion. And this is analyzed. And then, so this actually makes it very accurate. And biggest accuracy comes from detection system, the nuclear detection, particularly if you take something to energy of few hundred keV to MeV, you can detect a single ion separately, single atom. Actually, a lot of time STM, we detect picoampere. We are very happy. This is very fascinating. Even sub-picoampere is fantastic detection. But this actually is a attoampere. It is 10 to the minus, actually one ion typically has 1.6 10 to the minus 18 coulomb. Minus 19, like that, minus 8, on the range, if it is more charged, maybe minus, let us say, 5 minus 18 or maximum minus 17. But this kind of detection, independent ion, nuclear detection technique, that is how we detect our this energetic ions coming from space or during nuclear reactions, fragments we are studying. So nuclear technique is used for detection and steeper technique is used for steeping all kind of background. Okay. A negative ion production is used efficiently produced this carbon. So this is how actually it typically gives 1 into 10 to the power 15. Highest put it 1 into 5 into 10 to the 15 or 16 also sometimes. But 1 into 10 to the 15 is reasonably accurately available. Even 1 into 10 to the 14 is a very high rejection. So you can have this carbon which are decaying, or any element, if you have two isotopes, which is decaying with time, which is alive, which have a long time, you take the ratio and there we detect them. Okay. So, and so it is so accurate, when anything happens in the atmosphere like bomb blast or something, ratio goes here. So we actually have that correction also. We know how many bombs were there, blasted nuclear bomb. So we have that corrections also built in. So, so this is actually showing this whole system, and we have in this, we call it XCAM. This kind of size area it has taken, and this is the real one actually that we showed a schematic on how it works. And as I explained while telling that how the time is available. This is one important thing you will like. This is popularly I put. This is a shade of Turin, which was claimed this Jesus Christ used to use it. And so it is done by different AMS lab. It is in Nature. You can read the paper. You'll enjoy it. and 3 labs, Oxford, Zurich, and Arizona lab. With that time we are not in the picture. So did it, got the same date. So in science, that is the date, 1353 AD. And everybody will get science is science. One will not get something different. So, and you can make the conclusion yourself, but science is so strong. And then this is a kauri wood we did from some industry. And these are actually, there is in New Zealand, some catastrophic thing happened. Maybe major earthquake, even big earthquake. Earth has gone through lot of civilization process. And this whole, this, trees and all those things in certain region went down. And these are called kauri wood, which has got season over time. It has gone, and naturally it has some favorable natural condition. These are nowadays used in antique, very costly. So some company approached us, and we did the dating. But anyway, people are very clever. They get dating in another place also for checking. It was same, and it was 45 to 50,000. BP means before present, and present is for us is 1950, before atom bomb started pouring across. And they disturbed the earth, but the corrections are available location wise. Uh, and this is one of our own thing, Rakhigari nearby Delhi. Harappa, next, this in Haryana, it is there. And this we dated this Vaya with Pankaj and all these people, dated at different depth, and is popular. And then there are a lot of research papers, but this popular paper comes, as you know, in current science. So there you can see. And coming back to this I have covered this side, this high energy inelastic collision side. I will show one example which I like, and we become famous internationally also. When high TC started coming up, actually it was found that as soon as you give a good JC, actually it goes down. So some this thing was there. Lot of people who works on the surface said get abandoned. After some time, it is not going anywhere. But today, high TC cables are doing wonder. Even people are putting in the cable connection. If you see sun, this saved billions of dollars by high TC, the inserts to have the current inside the accelerator system. IUSC, we made a, I have not gone there because this is not my subject, but for example, world's first ITC 3.4 kilometer cable, we made a ECR beam. Till today, it is running. It was around 2000. And it's a new review of instrumentation, scientific instruments. You see, this title of the first, in from India first, in particular, was difficult to get accepted by journal. It is accepted, and we made it. So this flux spinning is that the spinning can be, once we understand the physics, it can be done by various techniques. There are a lot of reactors. You can give neutron, you can put reactor also, you can get. But we put in accelerator. Accelerator beauty is that we can calculate what is the flux. What is there? It is a type 2 superconductors. In fact, all superconductors, we type 1 actually have a lot of physics, BCS, all those things. But Nobel Prize also first one. But later it got type 2 superconductor, which are superconductor used. Because as soon as you put supercurrent, there will be field developed. Field has to be accommodated. So what happens typically, this Navium best one, if it is there, it actually makes few of the places, but it is still superconductivity quite stable because it has some dynamics. High TC actually, this superconducting region was narrow, and then so we cannot afford to have some perturbation inside the superconductivity. So what happens when type 2 superconductor, some field will be there with that. This field can be pinned to certain point. So then it cannot move around. So it cannot have a dissipative force, particularly for RF superconductivity. It is very important. So what we do? We ion beam, we produce, we know what is the coherence length. So we know typical diameter. Accordingly, we can choose the beam, energy, the curve, the location, and put the beam of that type. So we did the simulation. Even a lot of international lab also took from us. And you see this simple, this is superconductor if this Bismuth strontium calcium copper oxide, this is TC is higher, more than 100, 110 typically. Okay. So we could show that the reversible line, HT plane, HTJ, three-dimensional plane. So this is the region is superconducting, is non-superconducting. By putting a beam of few seconds, we could arrange the number of fluxon we can calculate. Suppose 5 Tesla magnet, 5 Tesla cosmos, how many fluxon? That many hole we created. And what is beauty is that it is experimental. This is shifted to this level. So what is simple physics wise? Suppose we are putting at this 2.5 or 3 K. So this superconducting vanishes at below 1 Tesla, 0.5 Tesla. It can go up to nearly 5 Tesla. So this is the big beauty. But physics again remains same if we show that. Because if I make some point non-superconducting, fluxon will be better there because if it goes superconducting and make it non-superconducting, you have spent energy. The basic theory is that if you get a better well, you get settled there, you will not go out of the well unnecessarily. So when you are in well and you will not get dissipative, when superconductivity is established, it will not move around. Because particularly high frequency system, cavity, superconductivity is established and fluctuates close to plus minus very rapidly. So I have done 10 giga, we have shown this was done with collaboration. Those are earlier one for India. This with this this Maryland. And then we showed microwave even up to 10 gigahertz. Actually, superconducting this thing gets dissipation, this absorption actually reduces. So this actually gets fixed to the point. This is called flux pinning the flux. In general defects of the planes, but it is random. Here, artificially, you can create that particular zone. But remember one thing, we should not overkill it. If we put too many, then we will have superconducting zone will be reduced, its total current will decrease. And we should underkill also, then it will loosen up. But so if one can exactly print, and then we can see also on AFM, we could see that we match the diameter, and it was matching reasonably with theoretical thing. So these are kind of accelerators which are developed in IUSC, and there is I like this, probably you have heard this, Raman, he is a very scientist, like Feynman, right? And he gave the name Goddam. It became God particle name. He also, anyway, he's Nobel laureate, no doubt, with quarks lepton. But his main thing is that he has thousands of hands. Their country will be known. Culture is scientific culture. By what kind of accelerator program they have, what kind of accelerator they have. So this way, India will not be left out. And if you carefully look internationally, each country developed, they have all kind of programs, accelerator also. But any country who are developed, so-called, and not going into war and all kind of thing, they have a big accelerator program. Whether you go to any country, Netherlands or Switzerland, so, even Italy or wherever, Portugal, and all kind of places, the big accelerator programs are there. And sometimes they don't have the space program, but accelerator program. Japan is very much, they have probably largest concentration of accelerators. But my another message is there are more than 30,000 plant accelerator, energetic anvil. 96% are used in only applications, only helping the industry and other application program. Don't do science with that. So that also put the impact. Knowledge of that can fit in various fields. People are there, they are going industry or various places. So there are this kind of opportunities are there. So it is not just like this field. So I didn't talk about other cat because that I talked confined in ion accelerator, the electron accelerator development was very important, one of the top accelerators lab in the country. But my ion accelerator, I didn't bring it. But they are also planning for future spallation source, making resonators. They have developed big facility. And all these places plus other programs together, we are actually working with industry. A lot of industry also developed due to us. And they are getting big order from outside, like cryogenics industry, cryo modules, cryo container. Because we cannot work in three shifts. We are scientists. We put our brain, develop design, test it. But they learn with us and they do in three shifts mode. They produce like ultra high vacuum chamber. And nowadays for span flat, ultra high vacuum chamber or many things, you don't go abroad. But slowly our country, actually we have a big market. They are market driven. There's most of the people buy low end. But once it comes, there are a lot of things will be developed in the country. But it's synergy with this thing. We have developed quite a few people who are doing big market internationally in this, getting international fund. L&T is one of them. ITER also I didn't mention. ITER is a mainly fusion program. But first, that beam is neutral beam is gone to the accelerator. They ignite and then they confine in a toroid and produce energy. It is not till now break even, but China is also having their own programs. This accelerator, high intensity accelerator, actually initiates the process. Like as I told, ADS. Main is reactor. Reactor is controlled by an accelerator. You can switch off also if you want. But reactors will be more useful, cost effective over time also. So this technology together with many other issues together actually make us better. As I saw now, one thing is the chips we know. Their accelerators use like anything, making and giving size down over time. But I didn't go into that. Those are known to everybody. But this is the important thing is that not only doing science, actually some other connected to industry. And this all labs, BRC is doing a big way. Yeah, for all this ISRO also. Nowadays, a lot of things are going to industry instead of them making. Because science and industry lab, one difference is there. This we cannot have so many manpower. And then once things are done, it is routine. So you have to run it. Accelerator running every day. Now we don't have to sit there. Initially, for 2-3 years, we had to be there, even sometimes overnight. But once it is done, then it goes to operator. Like pilot need not know how the plane fly. A bit, but not diver need not know how the car actually works. So similar way, these vendors are very important. That is one of the responsibility of national labs, vendor developments, and training their manpower to go all directions according to their choice. Thank you. So I think that's it.
So I think we have an excellent talk from by one of the pioneers in this accelerator physics, accelerator technology. So I see that there is a lot of interest developed in the students. Is there any other question left?
Can I ask a question, please?
Sure.
Yes.
That was a great talk, Dr. Kanjilal. I wanted to know whether the AMS system has been used for carbon dating of trees in India.
Yeah, many of the people are working on the carbon dating. Carbon dating, it's maximum use is done in carbon dating.
Yeah, but especially for trees.
Trees means generally it is done for dead trees. But
well, yeah, that's why I wanted to ask whether can be done for live trees.
Live trees also actually difficult is that it continuously getting from earth, carbon supply in different forms.
Yeah.
So and then carbon 14 part remains same. So until it is dead, actually this ratio will not change because carbon. But what is another thing is done? Yes, the important thing is that tree rings actually, some of the top rings gets dead later, all kind of thing. So ring-wise cutting radially, they are developed when these rings are formed actually. That is live tree, that is a good example. But this any wood or anything you take from dead tree, it is done very accurately.
Of course, that is true.
You are right, live tree we have to do separate section of the tree. Whole tree we cannot talk about.
Yeah. The reason I ask this question is very often, from a conservation point of view, a lot of trees get cut, saying that they can be easily replaced. And sometimes they cut down 100-year-old trees or something like that, saying, oh, that can be easily replaced by replantation, etc. But in some regions, it is very important that the trees are retained. And the one question which comes to mind, are this is not so old, so I mean, what is the age of the tree? So that is the reason I asked this
Very,
question.
very good question. This ring wise, that is very much done, and that is very uh,
Hmm.
known fact worldwide.
Yeah.
So you could quickly have some dating, taking ring wise separate section.
Thank
And
you. It
you
was
are
a
right,
great talk.
actually, it can never be replaced. This is a good thing people do. And that is why I think what we have got something, we have to put 10 times more.
Yes.
And we have to send photograph every year.
Yeah.
But sometimes people are not doing that also properly.
Yeah.
IUSC,
Okay.
we have done all of it.
Okay. Thank you. Thank you very much.
Any other questions from?
Yeah. So can I ask a question?
Sure. Coming.
Yeah.
Yes.
So, sir, thank you for the nice talk. You gave a very extensive details of the use of accelerators in various areas. So my question is also related to the previous question. So when you use the accelerator for AMS, it has to be very sensitive. So whether there is a interference from the previous sample, when you you are using different samples. So whether previously used sample can also interfere in the measurement, or what kind of care do you take to avoid that interference?
Actually, this we have first two layers also, we don't take it. Then slightly when it penetrates after few layers, when the stable ratio keeps coming, then interference decreases. But I will add something which I have not talked. Actually, this accelerator mass spectrometry, very intricate process is making samples. Graphitization, it is called, carbon. And this used to depend on very good hand to hand, means how good is the person to make samples, chemical processing. Now we have an automatic sample graphitization facility. And it is also now standardized. This we developed with ETA Zurich. They are the leader at this moment in this field. They have many AMS facilities. And if you remember that Palestine, Arafat's also, that polonium, all those things they did trace. And this now is independent of scientists, operators. The sample preparation test, sometimes error used to come. So that is now in IUSC, we have multiple. Actually, accelerator mass spectrometer, accelerator can take care of many samples. Many samples cannot be made. So we have multiple sample maker, and automata is fully processed. And then I told once that we have actually various samples between various labs. Sample is given by NIST. These are called standard. And we are very particular about that. We actually check the standard. So we are in the error zone, within acceptable error. It's a very small acceptable error, is very sharp. But we do it, and we are with this graphitization system automatic process. So sample making also, we used to have some initial error. And a lot of lab doesn't have this
Okay, sir. Thank you.
process.
Yeah.
So we standardize internationally. We interacted with them. Thank you.
So, I hope my question is related to what given the explanation. What factor can affect the ionization ionization process efficiency?
Ionization efficiency. Actually, one is physics factor, means how it ionizes the process. But here there are two types of ionization. We actually ionize to take from the cathode the atom and put attach the electron, attach electron by using cesium or rubidium. Okay. Rubidium we put in certain cases, cesium certain, mostly cesium we are using. But two ways. When it comes from this cathode, sometimes backside sometimes contaminations also come along with it. First is sputter and take. Suppose we are in copper ion. So sputter and copper cathode being copper, but there may be copper hydride and other form of copper. So this the cesium actually goes based on electron affinity, how much electrons are given. But later we are having a complete filter by a magnet. So there actually if this background goes out, but your efficiency comes if there are too much background, then lot of electron will not go. If there is a hydride which is more electron affinity, they will take preferably. So we sputter, clean it for some time, and then we start taking, and it gives a steady current. So it takes typically half an hour to start with, and once it is there, then it goes on. So this efficiency actually get parted. Efficiency is same physics process, but efficiency gets parted by contamination around. Anywhere, if something is static, there will be contamination. Whatever 10 to the minus 11, the contamination is there. Absolute vacuum, very high. So there when we consider Avogadro number, it's tremendous. So we tell 10 to the minus 10 is very, but it is not UHB, it is maybe close to UHB. Minus 11 onwards we talk. But background contaminations are there, still there. So similarly here we keep 10 to minus 3 typically when it's sputtered. So there are contamination. It depends what kind of environment. After some time outgassing, degassing, all those things happen. Contamination decrease, more cesium goes to the actual ion which we are taking. So stabilize also by that. But there is actually before going into the accelerator, nothing else can go. There is a strong filter, big magnet. So that is very important. You have the accelerator, you don't want any contaminant. Okay.
So one question here.
Yeah, so this is regarding this 15 UD15 electron.
Mm.
I was wondering what is the strategy of increasing the lifetime for the pulsing systems? What is the current status? And
Actually, we do some maintenance like we do in the car or something. Timely, typically 6 months to 1 year. We call it a maintenance breakdown. And the emergency breakdown means if something breaks, we have to maintain. If car develops some problem, we maintain like that. So we have this is running from 1989 till now, and ceramic life is practically very high. And I passed upon the metal to ceramic bonding a bit. I wanted to put it because I know some accelerators. I'm not taking the name. It had to be abandoned, and later I was called to see it. I thought it is a gone case. I saw it was bonded metal to ceramic, not ceramic, it was glass, no, sort of ceramic, not L2O3. And then bonding actually deteriorated. So if that gives time request. So there is a HVEC, earlier accelerator used to be made. They were using that technology. Luckily for us, we took a right decision and it was just coming and right time. And that is why I was there from full prompt in the accelerator, young physicist. So at young age, we can make some mistakes. We are very confident about ourselves. But Professor Patro actually was a great scientist. He helped us. And choosing also, I was involved. And I visited also different accelerator lab. So high voltage engineering was the dominating top company, and then American company, then NEC started coming. And we saw it has started with better technology. And this accelerator, as I contemplate with 100 years, it should not have any disturbance, maybe more. But maintenance has to be done. It has to be cleaned. Yes.
so you mentioned many times about STMs and STM.
Yes.
Is there any ever effort to combine STM and ion accelerator in India?
Actually, we had as I told, JP Singh actually did online some experiment. But important thing is that when doing this, we found ours is a center for national. We have around nearly 400 plus users. So they want to have a different thing. In IIT kind of system, we can have if we have one beamline to me. But there actually we have 12 beamlines around. But Pankaj is in some of the users, and we cannot distinguish who is better user or something. Some filtering is done. So they don't like something to be around this. And they want more space and sometimes. So putting an accelerator I found was a very sophisticated thing in a beamline. In synchrotron it is there because synchrotron can simultaneously feed wherever you are bending electron, you are having photon. And photon also you can disperse, you can just put. So there can be 50, 60 beamline simultaneously. But ion is once in a while up to one beamline. So when we put it, we find that after that person finish or something, I was selfish also, though I was overall with the control of the accelerator. I was leading the team. Being young also, was part of being director has many things to do. So do it, but I was seeing some injustice is being done. Somebody wants to do something, evaluation of the during sputtering. Somebody wanted to have blocking, different kind of experiment. They are occupying a big space, and my chamber has to be ultra high vacuum because this STM, not AFM. You have to do. You have to see the atom. Otherwise, you will not know the density of states and your tip, and you will not have a STS, scanning tunneling spectroscopy. Seriously. So we went with UHB STM, and probably that was India's first UHB. There was another one in Bangalore, but that is purchased from Omicron. But this is STM, Peugeot, everything was bought, even circuit. And we had it, but I will not very high-end experiment because that much time we are not having because shift is given after 3 shift, 4 shift. Somebody, I was trying to put some beam in the Hira, they go for 15, 17 days so that we can do some peaceful. But that also sometimes not as adequate. But it is a very STM, actually one of the things. I tell why nanotechnology comes. If you look carefully, this idea of nano was there from Feynman time onwards. So what is big, what happened is at the middle or higher other part of 80s when nano came. It is due to STM-AFM, practically. TM also reasonably that kind of thing was there. There directly you can manipulate, and these are some of the discoveries got Nobel Prize within 1 or 2 years. One is that scanning tunneling process, another high TC, like that. They actually changed the world concept and everything all on a sudden. So, and then why STM also ideas were there, going by Peugeot to the close and having the overlap of vacuum tunneling, so-called. Huh? So it was known. In physics, it was well known. It is not nothing. But simultaneously develop control that, as I told a bit weekly about passing on, the measuring that kind of current, tunneling current, individual one atom to tip of atom. So that also chip came around that time. Then controls this variation of small voltage, millivolt, to have Peugeot in angstrom range moving. That also stable voltage came around that time. So this technology is different technology developed. Once I did, physics idea was there, bang, the discovery. Like Higgs boson took 50 years. Because if this CERN accelerator was not developed, you cannot go few microseconds from the start of the universe, Big Bang. So that kind of energy density producing needed this accelerator. If it would not come, there was a disaster also. But important in science is that there are many things coincides at a point. The STM is one of them. And that gave bang to the field nanoscience. Now quantum science is coming later also for that way, having them together all qubits and coherent state. So important thing is in science actually these ideas come together, and most of the science, if you really plot, idea came first and then experiment. Most of the time, except very rare cases. So idea exists. The technology has to support. And together somebody has to understand, translate both. And some team has to work on this. Then thing happens. So this is a very good point. But there are now few STMs in the line. There are studies coming up in situ in the beam line. Synchrotron, it is very common.
Okay, so I think then let us thank again Dr. Kanjilal for the wonderful show. So we are so happy to have you. Actually, just one question I would like to ask. So this CERN is, I think, planning for 92 kilometers. So what is the plan for IUSC? Is there any plan?
Actually, that it so happened I am chairing India Sun Task Force. And last week also we had a Sun 70 years of completion. And for student, I forgot this. You can go for summer the school, but the Sun people think high energy physics. There are all kind of technology, all kind of physics. Go to science, any kind of mathematical techniques, all those things are there, and they are open. Their things are open. Access is open, and you can get also for 1 year, 2 year postdoc also various lines, detectors, all kind of development. And turn this on. Actually, funding is not assured. It is like this. It needs not 10 billion. It needs 100 billion. So this assurance is not coming. Intellectual physics wise, all kind of activities are going on. What kind of experiment, how they will plan, what kind of detectors will be there, and mostly all kind of proposals are coming. But until the signal comes from various government, actually this kind of project now, like ITER, they are done in a project, you become shareholder, something, or some fraction. And Sun is connected with GDP also. So we have to put a lot of money, but Sun, our people are doing excellently well. With the kind of money, we put very small fraction. And India has a lot of students. There is a recruiter. It so happens this, I have been chairing it for last 4 or 5 years. We have sent a lot of BTech also from IITs and a lot of engineering students, physics, for summer project or 6 months project or postdoc, different layers or employment also, tenure track kind of thing. So Sun 2 is on the way, but anyway, Ukraine is another thing, whatever. So all kind of thing happens in the world beyond our control. So, but it is physicist mind, it is there. And we would love to have it in future. Because this though I am not a high energy physicist, but listen, I can understand something. They still today, Higgs boson anyway, how mass came, it was a good thing. But dark matter, dark energy, which is a major part in the universe, which is seen in various ways, really experimentally proving we need that. And until we have it, we don't know how it will be done. There are cosmology, cosmic process also, there are some correlations in high energy physics, there are some overlap. But till now, there is no clear explanation. Higgs luckily didn't die. There is a rule that after dying, one cannot get Nobel Prize posthumously. So he got in time, 50 years wait. But this dark energy, dark matter, a lot of people contributed. But we don't know. Like Einstein could not see this detection of gravitational wave. So, but science is like that. It idea stays, and if it is quite obvious, people believe it. But until it is proven, it remains in the theory. So that is the.
So I think we would like to interact with you more, I feel, but students need to get their food in the
I
hostel.
know.
So we'd like to end the session. So maybe
I was surprised most of you.
Okay. So this is a small token of appreciation from
And my advice to all students and faculties, that become members, like member of IPA, and help it. So you can participate at various levels. It is in
And-
Bombay, it is spread all over the country.
So from IPA, Dr. Pankaj, I think we're happy to have you also. Thank you for your
also from there.
please.
So we can have one group photo there. So maybe what we can do, because they are already sitting, we can go to the
Yeah, people online, probably you can take care.
and then have it.
Tell them.
That's
It's okay. Thank you. It was a very good talk.
Thank you.
Okay, you can come back.
Okay, Dr. Kripamay, we are logging out.
Just once.
Yeah.
All right.
Okay.
Okay, see you then.
So I'll now stop the YouTube live also now. Okay.